Welcome back to the lectures on Hamilton-Jacobi equations. In the first lecture on Hamilton-Jacobi equations, we have basically introduced the equation and we indicated it comes from calculus of variations. And there are more general equations like Hamilton-Jacobi-Bellman equations and Hamilton-Jacobi-Isaacs equations coming from optimal control theory and differential gain problems. And we also see it's an equations in n plus some variable. One is the time variable t, and then n spatial variables x1, etc., xn, and hence the characteristic equations. If you go to the first order theory or method of characteristics, it will have 2n plus 3 equations, but due to the special nature of this equation, it can be reduced to rather it can be separated and decoupled to get 2n equations for xi and pi variable, that is du by dxi variable, and these are called Hamilton's ODE. We will see its connections to classical mechanics a little later, maybe in the next lecture or lecture after that. So and then we have seen two examples in the last class. One is the very simple equation, but there is no solution, classical solutions. But we have seen lot of Lipschitz continuous solutions. So if you demand solutions except on finitely many points, then you get solutions. But then you lose uniqueness. You also seen another example with multiple solutions. And the last example which we were discussing is about a time exit problem, more closer to our theory, which we were trying to do it. So let me quickly recall. So you have a domain, and this domain is 0, 1 cross minus 1 to 1, as you see here. And then you fix a point tx in this domain, and then look for all trajectories starting from tx. And then if you take the time, so the maximum time is 1. So look for the first time it exits this domain. So if it exits before the time t equal to 1, whatever time it thinks, and something like this. So you look at here. So if it exits like this, and then this is the time it given. On the other hand, it exits at the right end of this thing, and then tau is equal to 1. That is called the tau exit time of this problem. And what is your admissible trajectory? The set of all trajectories starting from tx and exiting it. Definitely it will exit at the latest time t equal to 1. So the maximum value of tau, the exit time is 1, and it can be before that. It can exit immediately if you want it. For example, it can exit like that. So tau can be anything between when it starts to that time. Okay. So now let's consider the minimization problem. So consider the minimization problem. Consider the minimization problem. What we consider is minimum of, you want to study at the exit time t to tau, okay, 1 plus x prime of s square by 4 ds. This is the minimum problem where x is in the minimization trajectory. You want to understand what is the minimum value, and you want to study the minimum problem. Of course, such kind of functionals you will see later. This is a functional defined on L of x prime of s, where eventually we will call L is the Lagrangian. You will see why we call it that one. More general things we will call it, but let's look at a typical example of Lagrangian. L can be in general, L can be a function of x of s, x prime, and maybe more s, you can call it thing, more general s's. These things you will see here. So and depends, of course, it depends on x and t, because x and t is fixed, fix x and t, and then you are trying to minimize this. Okay, so since the then definitely the minimum will depend on that one. So you so let's call this to be vxt. So vxt is equal to the minimum. I use the notation m because we will do integral t to tau L of, so in general it depends on all the numbers s. So let me write it L of, in this case L of x prime of s. Okay, L of x. But so what is L here? So L is a function from Rn to R. In this case you can think it as a one-dimensional function also. So you can think it as L is from, in case in more general things you can consider, L is from R to R, where L of V is equal to 1 plus 1 by 4 V square. Okay, so that's a Lagrangian which we are considering. It's a special case of a Lagrangian. So this you want to minimize it. We are going to prove something interesting. First of all thing. So you are looking for all the trajectories here. So let me, maybe I will draw the picture once again here. So in a different color. So I have a picture here. So I'm going to observe which is a claim which we can prove it here. So you have your trajectory, and this trajectories may be something like that. Of course this trajectory can be something like this. So what I am going to claim here, introduce a new trajectory connecting these 2 points. So this is your xt. So I will connect these 2 trajectory. So this is a linear trajectory. This is a linear trajectory. I call so this is your xt, x trajectory x of s, and I call this linear trajectory x tilde of s, which is linear. So introduce the linear trajectory. I'm going to this minimization problem to a minimization problem in Rn or R. You are going to minimize that problem. Okay, that's what is going to do it. So introduce the linear trajectories. X tilde of s is equal to, so it has to start from x plus some velocity. I will write precisely the velocity into s minus t. You see, and what is your v going to be, where your v is equal to 1 by tau minus t integral from t to tau and x of s ds. X is your given trajectory. So you are given x in AT. I introduce a trajectory in AT. So this you have to verify. That is indeed true, right? What is your x tilde of t? When x tilde at t, this vanishes, it is x. So this trajectory starts from x. And what is your x tilde at tau? X tilde at tau, it is tau minus t, and you will reach this tau point. Okay, so you will get the same x tilde of t. What is that? X tilde of t is equal to x. So it's a trajectory. So it's the same thing, same point. You will get it. You will get it. X at t. X tilde at tau. You have to calculate that. Okay, so x tilde, it will be tau minus t, so you will get the same value. Okay, so you will, it is the same trajectory connecting these 2 points. That's how you have taken as v in this way, because x tilde at tau will be tau minus t, that tau minus t, and that tau when you calculate the tau minus t and tau minus t cancel, and you will get here x tilde. So I think you have to take x prime of s. So here you have to take x prime of s. No. Okay. You have to take x prime of tau. So if you take that one, you will get exactly that x prime of tau into x tau. You will get it. X. Okay. and so it is a similar trajectory. So what is my immediate claim? This is an admissible trajectory. So you are looking at the minimization problem, and then you can see this one. So it's easy to see integral t to top x tilde, okay, L of x tilde, the problem L of x tilde of s ds is less than or equal to integral t to top L of x of s ds. So this is an important thing that you can see this. You can immediately compute this trajectory. So given any trajectory x, you construct a trajectory x tilde of s, and for that x tilde your energy is smaller. So it is enough. So this conclusion, immediately the conclusion is it is enough to minimize, because whenever you have a trajectory, there is a linear trajectory which is a straight line trajectory, and there the energy is less than the given condition. So it is enough to minimize over linear trajectories. Okay. That's an important thing. So you have a small exercise to do it immediately. Exercise. Therefore, the problem, minimization problem, so therefore the minimization problem can be reduced to a minimization problem over the reals. Okay, it's enough to minimize over V integral of tau minus t L of V. You see. So this is a minimization over V over R. So the problem of minimizing over trajectories reduced to a minimization over real. And you know how to, whenever to minimize over a real line, you look at its derivative, and then you can see that the minimum is achieved. So minimum is achieved okay, minimum is achieved when V star equal to, you can prove where the minimum. So you solve this problem. These are all part of exercise, because we will not have time to do all the exercise. Minimum achieved, you compute the derivative. You compute the derivative of this one with respect to V and equate, and that depends on x and t, and then you have to do that. So minimum will be 2 if x greater than or equal to t, and 0 if mod x less than t, and minus 2 if x is less than or equal to minus t. You see, so you get the minimum value. Minimum is achieved when V star is equal to, at that point, corresponding to that V star, this V star will give you the minimal trajectory x tilde. Minimal trajectory x tilde, minimal trajectory x tilde star, corresponding to that, because this is the slope. Corresponding to that, you can, with respect to that slope V star, you can construct your linear trajectory, and that's the trajectory where your minimum is achieved. And you can also compute these things. You should do to learn these things. You have to keep on doing exercises. We will learn. So you will do the exercise, compute then. Compute the minimum value, okay, Vxt is equal to 1 minus mod x. If mod x is greater than or equal to t, everything there depends on t, you see, and 1 minus t if mod x less than or equal to t. So this is the minimum point and this is the minimum value. Okay. This is the minimum point, this is the minimal value, okay. So you get it. So this function, so the next step you can show that v is a Lipschitz function, Lipschitz, but and differentiable, not all the points, all this you can verify, differentiable except when mod x equal to t, okay, except on this line segments mod x equal to t, you get a differentiability, and whenever it is differentiable, whenever v is differentiable, one can verify that v satisfies a Hamilton-Jacobi equation, satisfies let me not call it a Hamilton-Jacobi equation, Vt plus Vx square minus 1 is equal to 0, and it also satisfies the conditions, boundary and initial conditions. So this is, you know, that in that interval only x is in minus 1 to 1, t is in 0 to 1. And so you have your conditions, the initial and boundary conditions. This is the boundary conditions when initial Vt1 is equal to Vt at minus 1 is equal to 0 for all t in 0 to 1. Initial condition. So this is the initial condition, and b at 1x equal to 0 for all x when t equal to 1. So it satisfies the condition x is in minus 1 to 1. So you see, so you have minimal value satisfies a differential equation. This is something like a Hamilton-Jacobi equation. So this is what we are going to expecting to study. So you have your, so recall that Vtx is a minimal value given by L, a kind of Lagrangian. So in this course we want to understand with more general Lagrangians and its minimization problem, and then we want to see whether V satisfies the any equations. And this is a partial differential equations, and partial differential equations has a rich theory, and that is what we will be going to do it. So before that, what we will be planning to do in this right now is what is called another important aspects related to the minimization problem or a calculus of variation problem. So calculus of variations and Hopf-Lax formula. So in this now before we complete today's lecture, so we want to do that one, calculus of variations and Hopf-Lax formula in some general setup. Okay, Hopf-Lax formula. We'll try to derive it. Let's see whether we will have enough time to prove it today. So we will, so let me do the setup, admissible class. So first we want to do a minimization problem, admissible class first. So let me do it in a very systematic way. So you have your AT. So X is fixed for the time being. X fixed. And then Y is in Rn. Okay, X is in Rn and Y is in Rn. Y eventually you will be varying here. So you are considering, because Y is the recovery of your initial condition. So set of all twice differentiable functions C2 from 0 to T to Rn. So set of all twice differentiable functions, and at the initial value which will eventually vary is Y, and W at X T is equal to X. So these are the boundary conditions. So basically, if you look at the figure, so you have a domain here. Okay, this is your team. So at T equal to, so you have, so you are having two positions. So let me mark it here if you want it. Rn, you don't need this picture. So you have Y, you have X. So you are looking for all possible trajectories. So looking for all possible trajectories. Okay. All trajectory. That is what you are doing. So what is your minimization? So L is a Lagrangian given. Let. So that's a admissible class. So you are considering all possible twice differentiable kind of functions, continuously differentiable functions starting from V to X. And eventually, first you look at it for all points reaching there, and then all points reaching from all the points Y. So eventually we will vary Y as well. But T and X are fixed. According to that, I am defined, so you have a Lagrangian, and so what were all we are going to take here. L is from, so let me do this notation. L is from, eventually we will have conditions. Okay. Lagrangian. You will see why it is called Lagrangian later in classical mechanics. This is nothing but the difference in kinetic and potential energy. And G from Rn to R is given. These two are given. You will have conditions, okay? So basically you will have conditions of Lipschitz continuity for the given function. But here you need more conditions, which will come to that when we put in assumptions here. Okay, so this is given to you. So define the cost or energy functional. You call it cost or energy. It depends on the physical applications. Energy functional. J of W. Given W, that one, integral 0 to T, this interval L of W prime of S ds plus G of W at 0. Okay. W0, this term, if you look at it, this term is G of Y. Okay. So you can call you will see that this is a initial cost. So in physical applications, this is the initial cost. So your trajectory you want to reach, so you will to start a dynamics or whatever it is, you will have an initial cost, and these are the terminologies from optimal control we recall, and this is called the running cost. Because this is each time you have the total running cost basically. So what is your minimization problem? Minimization problem. Find W bar in AT such that J of W bar is equal to minimum of J of W, where W is in 80. This is what your minimization problem. Okay, some trajectory. So this is a calculus of variation problem where you want to minimize over the trajectories which you want to do it. Okay. So, and this depends on x and t. So we call this minimum value as uxt. Okay. So define uxt is your minimum value. Uxt is nothing but your j, because it depends on thing jw bar, that's equal to minimum of jw over w in 80. So eventually you will see u is a solution to your Hamilton-Jacobi equation, but what is the corresponding L? These are all the issues. So we have started with an L, which is a Lagrangian, which is a minimizing cost, and you will see a very specific examples later of this L. Okay, at least some 2 to 3 examples of which you are all familiar probably in calculus of variation we will be giving. So we are trying to give it in a slightly in a general setup. So this is your uxt. Okay, so you have your definition now, uxt. Okay, so now let me make my assumptions. These are all important. This you have to understand and should not remember. Assumptions. There are the main assumptions on L. So there are assumptions on L. Assumptions on L. And G basically we take it as a Lipschitz continuous function. So there are 2 assumptions. One, the mapping Q is in R. So you will be using these notations throughout my lectures eventually now, because these are all again coming notations used in the classical mechanics. To L of Q, this is in R, okay, is continuous and convex. Convexity plays a very big role. So you can study problems without convexity. So not that in applications all the time L is convex, then the problems are not generally complicated. As I told you, we are trying to derive very specific formula. So obtaining such specific formulas are not easy all the time. So in this setup we are going to derive a very specific formula for L. That's what I thought I will prove, complete the proof here, but I will not be continuity and convex. So this condition is very important, and the second condition is the L is coercive. This is another thing you have to understand very well, that is L of Q by mod Q, the limit is infinity. Limit mod Q, okay, tends to infinity is equal to infinity. So this condition means that L has see, mod Q tends to infinity, the denominator goes to infinity, but then L of Q should be more than the linear. Mod Q is something like linear, and if L of Q is also Q, then it will be Q by mod Q. It will not go to infinity. So that means L has super linear growth. Typically quadratic growth, super linear growth. So when n equal to, for example 4, when n equal to 1 in one dimension, if L of Q is equal to say mod Q, then that limit L of Q by mod Q is equal to 1. It will not go to mod Q is equal to 1. But you see, when L of Q is equal to Q square, this is a quadratic growth, then L of Q by mod Q goes to infinity as mod Q tends to infinity. So you need something more than the linear growth. In fact, you don't need Q square all the time. You can take Q is plus 1 plus alpha, something like that, little more than the linear growth or some other growth. It should go to infinity. And this is something like that. If you have a quadratic growth, something like you have convexity and quadratic growth, and you know that for things the minimum exists even in one dimension. You know such figure. So you have a function which is convex and continuous and a type which go into that one quadratically, then it will have a unique global minimum. So there are such results in one dimensions. So we want to understand it little more about it. So let me state a theorem. I thought I will prove the theorem also here, but I will not be able to complete the proof here. So theorem, that is what the Hopf-Lax formula. Hopf-Lax formula. So maybe I will try to prove, maybe I will to take little extra time. Okay, so assume, okay, L as above with the with the above conditions. Maybe you can assume G is Lipschitz continuous, which we are anyway going to do it. Lipschitz continuous, then U can be given by a formula uxt is equal to infimum over y in Rn. At present, G Lipschitz continuity may not be necessary, just continuity will do, but since we are working with Lipschitz continuity and we are assuming that really may not be necessary for this particular representation, y in Rn of T L of x minus y by T plus G of y. You see? So you have your solution, and this is called the Hopf-Lax formula. Maybe I'll try to give a quick proof so that I don't have to recall here. The other properties I will recall it in this thing. So let me try to give a quick proof of this. Some ideas we already introduced, so we will do this thing. So let y is in Rn, x and y are already fixed. So you see, this is a minimization in Rn. You have to understand the difference. Here you are having the minimization over a class of trajectories. The minimization is over a class of trajectories. But then that minimization, you are reduced to a minimization over the, you see, the minimization over Rn. So here is your minimization. You see? So the minimization changed to Rn, and this exactly what we have seen it. The earlier example, we minimized that one. So it's a representation with the general L. It's not that one particular L. So what you require is this property of the convexity and coercivity. And both plays a crucial role in this representation. So that's why let me give you a quick proof of it. So you start with the y in Rn, and then look for the linear trajectory. Consider the linear trajectory. Okay, consider the linear trajectory. X tilde of maybe. What is the we are having using W? Yeah, we are using the notation W. So let me use W tilde trajectory. W tilde of S is equal to y plus S by T. That's a slope I am taking into x minus y. This indeed W tilde of 0 is equal to y and W tilde of t, s by t is t by t is 1, x and y cancel, this is x. So that implies W tilde is an admissible trajectory. And then uxt is the minimum. So uxt is the minimum of that trajectory. So any other trajectories, the cost will increase. Okay. So therefore, uxt has to be less than or equal to j of this w tilde, because uxt is the minimum among all the trajectories, and that's nothing but integral 0 to t L of w prime of s ds plus g of y. But then w tilde, because you are taking, but w tilde of prime with respect to s is nothing but x minus y by t. So this w tilde of s minus is nothing but x minus y by t. There is no s there because this is a linear trajectory. So that is less than or equal to, so that will come out, and then you integrate, you get t L of x minus y by t plus g of y. You see? So one way you have proved, you want to prove this infimum. So for every uxt is less than or equal to this one. That's what we have seen now. Okay, you have to prove the reverse inequality. So one inequality you will get it, and then you prove for every other trajectory. So now conversely, okay, you compute t into L of x minus y by t plus g of y. Please go through the proof before reading the g of y. This is equal to t L. So I do some trick here. This is 1 by t, and then integral of 0 to t w prime of s, any w, for any w, conversely let w belongs to, this is not linear trajectory. So w prime of s ds plus g of y. But integral 0 to t w prime of s ds, this one is nothing but wt, and that's what you want to this one, okay, right? It is wt and g of y dy, and this is less than or equal to, that's what you use it, and this is writing it as less than or equal to, and you apply what is called Jensen's inequality. Once you have a Jensen, so this is an average, and you can put it inside, and then you can take L inside. Okay, so this is just a computation, because this will be wt minus w0, that will be x minus y by t. So I have not done anything here. What I have done, important thing is to taking L inside. When L inside, t and t cancels, and it will be 0 to t L of w prime of s ds plus g of y is nothing like w0. You see, so you have this inequality proving it. So by Jensen's inequality, this you should know. When you can apply Jensen's inequality, please refer some other book, Jensen's inequality. Okay, once you have this one, what you do is that why you have fixed it, minimize over, first minimize, there is no w here now, first minimize over w, and then minimize over y, and then minimize over y. Okay, so if you do minimize over W and then minimize over Y, you will exactly get your minimum integral of t L of x minus y by t plus g of y, and the right hand side is minimum by definition. That's nothing, the minimum is nothing but uxt. Okay, this is by definition, and that's exactly you want to prove it. Okay, so I will stop here. So what we have done is that maybe we'll recall again that every solution, the minimization problem over trajectory reduced to the minimization of the Euclidean space. And that you can, so this trajectory minimization reduce this formula. This will allow you to get the solution expressly in a very specific way, because you can differentiate and you can get explicit solutions by minimizing over this one. Okay, so I will stop at this stage and we'll continue the lecture in the next class. Thank you.